Good day everyone, my name is Benedict Itonga, BSEC3A. Today I am going to discuss about transmission line parameters, or just simply line parameters. The first parameter is the velocity of light, Vc or c. The absolute velocity of light is only a function of the absolute permeability and the absolute permittivity of the medium. The velocity of light can be calculated by this equation here, which is equal to 2.9979 times 10 raised to 8 meters per second if it is in free space or vacuum. However, if it is not specified in the problem that you are using free space in vacuum value, it is assumed that it is 3 times 10 raised to 8 meters per second. Note that the impedance of free space is this value in ohms, the permittivity of free space is this value in farad per meter, and the permeability of free space is this value in Henry per meter. These values here can be found in your scientific calculator because they are constant. If you want, you can check YouTube for how to find this, but it is simply at the cover of your calculator, so it should be fine. This is the equation for calculating the relative permeability of the line here. And this is the equation for calculating the absolute permeability, or rather the relative permeability of the line right here. The next parameter is the velocity of propagation, or the VOP. The velocity of propagation is of a signal in a transmission line is the speed at which the electromagnetic energy travels inside the line. In most cases, equal to phase velocity, or VP. We will discuss this one later. The velocity of propagation is equal to the speed of light divided by the square root of the relative permeability multiplied by relative permittivity. It is also can be also calculated in 1 divided by the square root of the prime inductance multiplied by the prime capacitance, L prime C prime. Excuse me. Most mediums have a relative permeability of 1. So, the velocity of propagation can also be calculated by the speed of light over the square root of the relative permittivity, or speed of light over the square root of the dielectric constant here. We'll move on to the third parameter, which is the velocity factor. The velocity factor is the ratio of the velocity of propagation of a signal and transmission line to the velocity of light in a free space, which is this equation. Vf is equals to VOP over C. Vf is equals to, if you elongate this further, the velocity factor is equals to 1 over the square root of the relative permeability multiplied by the relative permittivity. But as we know, most mediums have a relative permeability of 1. So the velocity factor can be solved by 1 divided by the relative permittivity, or 1 divided by the square root of the dielectric constant. You must remember that the velocity factor in free space or in a vacuum is always equal to 1. Now to our next parameter, which is the velocity of electromagnetic wave. Light is an electromagnetic wave. Therefore, the speed of EMW is the same as the velocity of light, which is 2.9979, or 3 times 10 raised to 8 meters per second. Now facts. Sound is a mechanical wave, longitudinal in nature, while light is an electromagnetic wave, transverse in nature. Sound travels faster in more dense mediums like water and glass, while light travels slower in more dense mediums. Conclusion: electromagnetic waves travel slower than the speed of light in a transmission line, which is the velocity factor must be less than 1. And here we are, the propagation constant, which is this symbol. It is a secondary line constant, a measure of change undergone by the amplitude of the wave as it propagates in a given direction. This is the equation for calculating the propagation constant. it should result into this form, which is propagation constant must be equal to the attenuation constant, which is the real part, and the phase constant, which is the imaginary part. As stated here, R is equal to the resistance, L is the inductance, the G is conductance, C is capacitance, while this symbol here is just 2 pi times the frequency. If you see this letter J, or in your calculator it is I, it means that this part is the imaginary part of the equation. Now we will discuss about the attenuation constant very briefly. It is a secondary line constant. It is the real part of the propagation constant. The larger the attenuation constant, the more lossy the line is and the faster the wave decays. But if the attenuation constant is equals to 0, then the line is lossless. It is measured in Nepper per meter or decibels per meter. 1 Nepper is equals to 8.686 decibels. Let's proceed with the phase constant. It is the imaginary part of the propagation constant, as we said earlier. The phase constant is calculated exactly the same way from capacitance and inductance per unit length, regardless if the transmission line is lossless, lossy, or distortionless. It is measured in rads per meter or degrees per meter. For a lossless line, it can be determined from the phase velocity, or Vp. Now, this is lambda, or wavelength, of the signal within the transmission line. Vp is the phase velocity. This is the absolute permeability of the line. This symbol is the absolute permittivity of the line. And the F is frequency of the signal. The wavelength can be calculated by 2 pi over the phase constant. The phase velocity is this symbol over phase constant, which is 2 pi f, or frequency, over phase constant. Now, phase constant, if you rearrange this, can be calculated as 2 pi over the wavelength, or 2 pi f, as if you rearrange this, 2 pi f over the phase constant, phase velocity, I'm sorry. Or simply 2 pi f multiplied by the square root of the absolute permeability and the absolute permittivity. Now, wavelength. As we discussed earlier, this equation here, frequency doesn't change when a signal encounters a different material. But due to transmission line effects, the wavelength changes. The change in wavelength compared to free space is inversely proportional to the velocity factor. Right here, as we discussed earlier, is the equation for wavelength. Also, like this, wavelength is equal to 2 pi, and this symbol multiplied by the inductance prime and capacitance prime. As we know, this symbol here is equals to 2 pi f, so it will cancel the 2 pi, and it will result to the wavelength is equals to 1 over the frequency multiplied by the square root of the inductance prime and the capacitance prime. In a transmission line, the wavelength is equal to velocity of propagation over frequency, while in free space or in a vacuum, the wavelength is equal to the speed of light over frequency. Now we will talk about the phase velocity and the group velocity. Just brief. The phase velocity is the speed at which a point of fixed phase propagates. This is the velocity at which the phase of any one frequency component of the wave travels. Usually, it can be considered equal to the velocity of propagation, but not always. The red dot shows the phase velocity here. As you can see, here, the red dot, it is much lower than the green dot. The green dot is the group velocity. The green dot below shows the group velocity. The group velocity is the speed at which the electromagnetic information travels. The velocity with which the overall shape of the wave's amplitude, also known as the modulation or envelope of the wave, propagates through space. The group velocity is always less than the speed of light. But even if it is less than the speed of light, it is always faster than the phase velocity. Sorry. Now, this is the equation for solving the group velocity, which is the group velocity is equals to the speed of light squared over the phase velocity, or Vp. Oh, sorry. Now, this is the equation for solving for the lossy line, the characteristic impedance of a lossy line, and the propagation constant. For lossy line, the phase velocity or Vp is a function of frequency. But this is bad. The Vp is equals to pi f over beta. If the different frequencies that comprise a signal travel at different velocities, that signal will arrive at the end of a transmission line distorted. We call this phenomenon signal dispersion or simply dispersion. You must always remember this equation for solving the characteristic impedance of a lossy line, also the propagation constant of a lossy line. While solving this characteristic impedance and the propagation constant in a lossless line is different. In lossless line, the characteristic impedance will be purely resistant, since the imaginary part of the formula will cancel out. As you can see here, both the R prime and the G prime, the resistance and the conductance prime is equal to 0. So if this is equal to 0, the imaginary J and this symbol, the 2 pi f, will cancel out, leaving only the characteristic impedance equals to the square root of L prime and C prime. The propagation constant will also transform and will only be imaginary. The attenuation constant or the real part will be equal to 0. Solving it is equals to the imaginary part times 2 pi f multiplied by the square root of the L prime and C prime. This is discussed earlier, the beta, the phase constant, the wavelength, and the phase velocity. Now, I will show you an example of how to solve a problem using a lossy line. This is a computational problem to solve the propagation constant and the characteristic impedance ZO of a lossy line. Now this is my given. The R prime is 64 ohms. The conductance G prime is 0.58 Siemens. The capacitance is 62 picofarad. And the inductance is 75 nanohenry. We have a 100 megahertz frequency. And this symbol, 2 pi f, shall be equal to 200 times 10 raised to 6 pi. Now, part 1, solving for the characteristic impedance. As you remember, for solving in a lossy line, wait here. Yes, this. You must always remember these equations, because this equation here, we will use this for solving the characteristic impedance, and this will be the propagation constant. Now here, since you can't divide the complex number as it is, you can't divide this. You must convert the rectangular here to polar form. Here I am converting the 64 plus j15 pi to its polar form, as well as 0.58 plus j 0.0124 pi to its polar form. Then we will insert it back to the equation, and then there we will divide it, because in polar forms you can divide the equations. Just divide this real part, this here and this here, while the angle you just minus it, just subtract it to each other. 36 point something something minus the 3 point something something there is equals to 32.5221 degrees. And if you want to know what is the square root of this polar form, first you will get the square root of the real part here, and to get the square root of the angle, just divide it by 2. This is square root 1 over 2, which here. This is the polar form of the characteristic impedance. Now, we will convert the polar form into a rectangular form, but you can just get this as your final answer as is, but For the sake of explanation, we will convert the polar to rectangular. Here is the equation to convert. Yes, this is equation to convert, sorry. This part here. So converting this polar form will result to this final answer in rectangular form. Okay, if we're done with that. Now part 2 is the solving for the propagation constant. We'll rest this here. This is fairly easy because it is you can just input it directly. But of course, since we're dealing with the complex number, we can just divide it as it is or get the square root of it as it is. We have to convert it back and forth so that we can compute it correctly. This is the equation for the propagation constant. Of course, we insert our givens and we will simplify it resulting to this. Since we can't what do you call this? We can't get its square root since it's a complex number and there's an imaginary part. There's no square root of imaginary. We convert the rectangular form to polar form. So converting it will result into this polar form. And we insert it back to the square root line, to the equation, I mean. Now, since it is in polar form, we can get its square root. All you have to do is get the square root of this real part. And to get the square root of the angle, just divide it by 2. So this is the final answer in polar form. Now, for the sake of explanation, again, we will convert it back to its regular rectangular form. So this is the equation. It's just the same. And this will be the final result. And that is my final answer in rectangular form. Since the given is in rectangular form, the final answer must be in rectangular form for me. But you can just stop here because these two here and these two here, this here and this, they're both the same. It's just different forms. Now, thank you for listening to my explanation in line parameters. I hope you learned something from me. And thank you again. Good day.